class. Today we're going to go over relations and functions and how to identify them, and then we're going to talk about a little bit of graphing at the very end of this handout over down here. So for right now, let's go ahead and get into this. And let's talk about what a relation is. A relation maps two different sets. All right, that's what a relation does. Now, you note that I'm saying a relation. A function, on the other hand, a function is a relation, right? Note that all functions are relations, but not all relations are functions. A function is a relation that maps a set called a domain to a set called a range. And further, this mapping must have an unambiguous predictive quality. So the two key words here are predictive and unambiguous. So basically that means if I give you a piece of information, you can absolutely tell what the next piece of information should be. So let's come down here and let's look at this first illustration here. This is just kind of what you might expect to see at a menu. And you can see, if you want to get a burger, that's $5. If you want to buy chili, that's also $5. If you want to buy fries, well, then that's $3, right? The menu items are the domain, and then the prices are the range. You tell me what you want, I can tell you the price. And so it's got a perfect predictive quality in that nature, in that any item has its own associated price. Now, what if I said, all right, I spent $3, can you tell me what I bought? Well, yeah, if you spent $3, then obviously you bought fries. Now, what if I said I spent $5? What did I buy? Well, I don't know. You could have bought a burger, or maybe you bought chili. It's ambiguous in that case. So note the predictive quality goes in this direction, but not the other way. All right, so that's what's required. It has to be predictive in this direction right here. All right, so this is what's called an onto function. Right? That means every element in the domain and every element in the range are both used. All right, and so what is the domain? We've got a burger, we've got chili, and we got fries. What's the range? $5, and then $3. Okay, and that's it right there. Okay, now we're going to go to this guy here. This is a one-to-one function. All right. So note that for every element in the range, that is mapped, it has only one element in the domain going to it, right? So it kind of, in this one, for it to be one-to-one, there is a predictive quality going in the other direction. And so the domain of this is simply x1, x2, x3, and then the range is y1, y2, y3, and y4. So this is what's called a one-to-one function, but note that it is not on 2. Right? It's not on 2 because this guy is not being used. All right, now let's look at this one here. Note every element in the domain, every element in the range. This is there is all involved in the mapping, so it is both a on-to. And then note that there's only one arrow for each element in the range, right? There's not anything extra. So it's also one-to-one. And usually in this class, if we come across a function that is one-to-one, almost always it's going to be both onto and one-to-one. But noting the difference is can be important, particularly if you're trying to program something in the computer. This is where things where these differences in definitions come into play. Usually in graphing, you'd be pretty hard pressed to find a function that is one-to-one but not onto. All right, so the domain, well, that's going to be 2, 4, and 5, and then the range will simply be 1, 3, and 4, and that's it. That's how it goes. All right, down over here, the next one we have a table. Note for this is a domain. I'm just going to use a capital D for domain, and then a capital R for range, right? We got the domain and then the range just like this. So we want to know first, is this a function? Well, so first off, we got to figure out, for it to be a function, remember it's got to have that predictive quality, right? There can't be 2 elements in the range, for one element in the domain. Like you can't have, if fries go to $3 and $6, right? That wouldn't make sense. I mean, not thinking about different sizes. The same size of fries, $3 or $6. Well, that menu wouldn't make sense. And so that's what we're looking for, right? Everything in the domain must go to one and only one element in the range. So we've got to go through all these, x's. Note that all these x's here, are all different. So we're not repeating anything domain, so that's okay. And so you can see that because of that, everything in the domain is used only once. Now, if this were not, so yes, this is a function. Now, if we had like another 15 and then we had an 11 here, if something like that, then it would not be a function. But okay, so what is the domain? Well, the domain is simply 0, 2, 3, 5, 8, 10, and 12. And then the range, and note that the range, you can repeat numbers and that's fine. It'll still be a function. Okay. Find f of 2. So we just look at this guy here. F of 2 is 0. Find f of 5. Well, that's there. F of 5 is 3. Find f of 12. Well, that's this guy here. F of 12 is 8. And that's it. All right. Hopefully it's pretty straightforward. If not, you may email me any questions on this. Plot the following relation and determine if they are functions. Okay. So let's go ahead and plot this guy. We've got the set of ordered pairs, -2, and the y value would be -2. So it's -2. Put that right there, right? We just plotted that point. Now let's plot this point. -1, and then 0. So it's plotted right there, right? So note these are just ordered pairs. 1 and 0. That's right there. And then we've got 3 and 3. So you go to the right 3 and then up 3. All right. So I want you to kind of notice something. You can kind of tell just by looking at this whole plot here. That the x's aren't repeating. We aren't getting multiple values of y for one value of x. So clearly, it is a function. But note that if it, let's say it did, let me go ahead and, what if we had another 3 here and then say that was 1? Well, then we would have another point right there. And if this were the case, you'd see, well, you got 2x is going to 1, I'm sorry, 1x going to 2 y values. And you look at the graph, you notice that these 2 points would go, would both be in the same vertical lines. It's called the vertical line test. It's a quick way to determine if a plot of a function, of a relation, is in fact a function or not. Okay, so we don't really have that point. That wasn't part of it. You can clearly see that, yes, this is a function. All right, so let's look here on the next one. We note that we've got 2 different x's going to 2 different values of y. So this is definitely not going to be a function. Let's go ahead and plot these. Negative 2 for the x, negative 1, and then another one here. And now let's plot this guy, 0 and 2. And then finally this one, 2 and 3. And so as you can see, this fails the vertical line test right there. So you don't even have to look at what the numerical value of the points was. All you have to do is use your eyes to see that the graph is going to intercept a vertical line more than once. All right. And here we have, we see the vertical line test spelled out in print. If any vertical line intersects the graph of a relation at more than one point anywhere in the graph, then the relation is not a function. Note, it is still a relation, but it is not a function. Okay. Are the following graphs functions? Fails a vertical line test in quite a few different places. So, not a function. And note here, no matter where I draw, I only intersect the graph once. So yes. And so note on this one here, it passes here, but fails all along here. So this is not a function. All right, use the graph to answer the following. So this is kind of like what we're doing with the table, but we're just going to use a graph instead. So we got f of negative 1. So you go where x is negative 1, and then you go up to see where you intercept, which is about there, so you put a 1. Find f of 2. We go where x is 2, we go down, find the y value, plug that in. Find f of 1 plus f of 2. I'm sorry, f of negative 1. So note that we've already worked these out, right? F of negative 1 was here, that was 1. F of 2, well, that was right here, and that was negative 2. So we just got to add those two together to get negative 1. All right, and so again, on D, now 2 times f of negative 1, well, that's just going to be 2 times 1, which is 2. Right, just like that. All right, find f of negative 2 plus f of 3. So note that this is inside the parentheses. So we got to evaluate what's inside the parentheses first. So we get f of positive 1. Okay, and then what is f of positive 1? We come down over here, figure out where the graph intercepts. That looks like that's going to be negative 2. All right. What is the domain of the function? Let's say we've got a filled-in circle here and it's a hollow circle here, like so. If that's the case, which it is, we're going to say the domain, bracket, negative 3 to positive 3, open parentheses. That's it. That's the domain. Alright, so now that we've gone over what a function is and kind of some basics of graphing it and reading the graphs anyways, let's look at a set of functions that we're going to go ahead and call these the toolkit functions, right? And the reason I'm calling them the toolkit functions is because these are the sets of functions that you should have the shape of the graph memorized. Just like when you read a word like dog, a picture of a dog should emerge in your brain. When you look at these equations, a picture of the equations should instantly emerge in your brain. That's the kind of recognition you need to have for these in order to do well, both in this math class and future math classes. So let's go ahead and take a look at these. This one is called a constant function, right? You know, it's y equals f of x, which is just some constant, right? So basically, it doesn't matter what value of x you're looking at. Y will always be the same value. And so you see I have this graph. I'm using desmos.com as the website I'm using. Let me go ahead and right there, Desmos, get in the screen. Okay. So that way you can, and I will have a link to these in the module. But basically you can see that it doesn't matter what value of x we assume, y always has the same value. Right? The output is always x. The output is always 1. Where it doesn't matter what value of x you put in. Right now I've got the constant set to 1. I can, of course, put any constant I want, and the effect is still the same. Alright, so the next one on the docket is what's called the identity function. Alright, so this basically, the identity simply means it doesn't matter what value of x I put in, y is going to be the exact same thing. The reason it's called the identity function, we've dealt with different types of identity operations already. For instance, the identity of operation for multiplication is 1, right? You can multiply 1 by anything and you'll still get the same number. The identity operator for addition is 0. You can add 0 to anything and you'll still end up with the same number. And so for this one it's the same thing. It doesn't matter what value you stick in, you will always get the same output. So this is again the identity function. Right, this is the constant function. Okay. And then for the identity function, let's go ahead and take a look at the graph. As you can see, the graph makes a 45 degree with either axis. 45 degrees here and here. It does not matter what value of x you plug in. The output value for y is always exactly the same. Okay. Again, so that graph basically just looks like that. Next, the square function. And I got my screen up right now so I can switch between the monitors. I apologize for the resulting handwriting there, but that is square, is what that says right there. Alright, so let's take a look at the graph now. So the square function just means we do this operation. We take the square of the input, and the function looks like this right here. Right? We all know what kind of shape this is. We've probably all heard the word parabola before, and that's exactly what we're looking at. Parabola, it's got a very specific geometric definition. We'll get into that later on, but for right now, just know that this shape is a parabola, and anytime you see this, that means you took the square of something over here. Alright. So note the domain and range. You can put whatever you want into here and it will work. If you plug in a negative number into the function, note what it does. A negative times a negative is a positive. So we end up, for any negative inputs, the output is positive. The only time it's not positive is when they are both, in fact, 0. All right. So again, the function looks like that. All right, the cubic function. The cubic function, note that is simply a number multiplied by itself 3 times. If we plug in a positive number, well, that will be a positive output. If you put in a negative number, a negative times a negative is a positive, but then you multiply it by a negative again to get a negative. So you will have some negative outputs. Let's take a look at it. As you can see right here, this is what it looks like. You're just taking the number, multiplying it by 3 times. Note that the domain is negative infinity to infinity, and the range is the same thing, negative infinity to infinity. Note this function is always increasing until you get to this point where it pauses, and then it starts to increase again. Okay. All right, and again, it looks like that. All right, the next one is called the square root function. Not original, I know, but none of these names really are, but they are descriptive. All right, so note for the square root, we're restricting our output to real outputs, right? If I take the square root of a negative number, I do get an output, but it is imaginary. So we're only interested in the real output. So we would say that the domain for the square root is from 0 to infinity, right? And the range will end up being the same thing. We can put in 0, but we cannot put in any number less than 0. So from 0 to infinity, that is our domain. And let's take a look at it. And note that it looks kind of like half of a parabola on its side, right? And the reason it looks like half of a parabola that is lying on its side is because that's exactly what it is. Note that if I were to graph the relation y squared equals x, you do get exactly a parabola on its side. Note this is a relation, not a function, though. All right, so that's what that looks like. Let's move on. All right, this next one is the cube root function. Basically, you're saying, what times itself 3 times gets you the result. For instance, what is 8? The cube root of 8? Well, it's 2, because 2 times 2 times 2 is 8. The domain for this can be anything, because if I said, what is the cube root of a negative number, say negative 8, you would tell me it's negative 2. So let's go ahead and take a look here. And so note we got this little S shape going on there. So the domain is all real numbers, and the range is also all real numbers. All right, so y equals 1 over x. This is an inverse function. Right? No matter what you plug in, the output will always be the multiplicative inverse of that. So if you plug in 2, the output is 1/2. Note 2 times 1/2 is 1, making it an inverse. If the input is 10, then the output is 1 over 10, the inverse. So that's why it's called the inverse function. Note that x cannot equal 0. If you plug in 0, you get something that is undefined. The closer you get to 0, the higher the number will be, right? So let's go ahead and take a look. All right, so note the closer we're getting to 0 here, the higher the value is getting. Higher and higher. So if you plug in 1, that's 1 over 1. If you plug in 1/2, well, then you get 2. If you plug in 1 divided by 10, well, then your output will simply be 10, which is way up here. And so you note that it's shooting up faster and faster and faster the closer you get to 0. And then also note, the same is true if you approach 0 from the other direction over here. Okay? And then this next one is the inverse square. The shape is very similar. Except it's going to approach infinity faster when you get closer to 0. Let's go ahead and just plot two different versions of these. We got y of x and we got g of x. Okay, so like I said, very similar shape, except note the square kind of forces the left-hand side to be north of the x-axis here. And so you can see that g of x is shooting up towards infinity much faster, right? And then at 1 and at negative, well, at 1 they meet. These are on the same side. Note they have the same magnitude here, but and note that after that, 1 over x squared is slamming down into the axis much faster. It's important to note that it will never reach the axis. Right, we can go way, way far out. That looks like these. If you look right here, it looks like it's about touching the axis. But if we zoom in really, really close, you will begin to be able to see a little bit of daylight. In between. It's not quite as obvious here, but you can definitely see it. There we go. See, like I said. So it looks like there's quite a bit of a distance in between these two, but look at the scale that we're dealing with here. And also note that at this scale, the green, the f of x is still way up here. Okay. And then, very similar on the left-hand side, except now the inverse square is up high. Alright, so once again, this function looks like this. And then this one looks like this. Alright, and do the same for these other ones, but we saw them on Desmos. Look for that Desmos link in the module. If you have any questions, email me, and have a great day.